Cool. All right, we're going to continue our discussion of alcohols, our reactions of alcohols, and specifically we're going to focus on substitution reactions. Okay. So substitution reactions means that we're replacing one functional group with another, right? And so if we're talking about substituting alcohols, that means that we start out with our alcohol. All right, we're going to see that we're going to be doing these nucleophilic substitutions. So I'm going to use some generic nucleophile here. And what we're going to get is our nucleophile substitutes that hydroxide group, that hydroxyl group. Okay, but unfortunately it is not this easy with alcohols. You don't just take your alcohol, mix it in with the nucleophile, and get a substitution reaction. All right, there's something kind of wrong with this scheme here. And that is if our nucleophile attacks that carbon, and I guess to be clear here, right, we talked about sort of being able to see a little heat map in terms of where our electron density is here. If I'm looking at this molecule, where is the majority of the electron density in this molecule? On that oxygen, right? So this is the one that's kind of glowing red, and this is a polar bond. It's taking electron density away from both that hydrogen and that carbon, okay? So what we would sort of expect with our substitution reactions is our nucleophile attacks that relatively electron deficient carbon and kicks off that leaving group so that we don't have too many bonds and we don't break carbon's octet. Okay? The problem here is that our leaving group would be the hydroxide ion. All right? And in the grand scheme of things, the hydroxide ion is a bad leaving group. Okay, strong bases are bad leaving groups. Hydroxide is a strong base. And again, strong base equals bad leaving group. Okay, so in our reactions of alcohols, our substitution of alcohols, we can't just simply add in a nucleophile and displace that hydroxyl group. It's not a good leaving group. All right, so we're going to have this strategy that we're going to use over and over again for these reactions of alcohols. What we're going to do first is we're going to convert that OH into a good leaving group. And then we can add in our nucleophile and get our substitution reaction. All right, so when we're substituting alcohols, really we're going to swap out that OH group for a better leaving group, and then we can do our substitution reactions. And we're going to have a few different strategies of doing that. Okay, so the first is to use what would be our classic good leaving group, our halogens. So the first method is we're going to learn how to convert an alcohol into an alkyl halide. All right, and we need something kind of fancy to do it basically, because like we just discussed, our simple nucleophilic substitution reactions aren't going to work. All right, so let's take an alcohol here. Notice that we're starting with a primary alcohol. right, we can convert this thing into an alkyl chloride. All right, but again, we got to use something kind of fancy to do it. We use what's called SOCl2 or thionyl chloride. All right, these reagents are kind of nasty, expensive reagents. They're difficult to use. They're highly reactive, and again, that's because they're sort of catalyzing this substitution reaction and allowing us to get rid of that OH group, which is kind of stubborn and a bad leaving group. We're not going to sort of look at the mechanism here for this particular reaction, but kind of suffice it to say that that SOCl2 globs onto that OH group, making it a better leaving group. All right, so again, that's going to be a common theme that we see, is we got to make that OH group into a good leaving group. And we can do the same thing, converting it to an alkyl bromide, again using something kind of fancy, PBr3, phosphorus tribromide. All right, now let's take a secondary alcohol. Okay, we can actually do the exact same thing to our secondary alcohol. Okay, but importantly, our secondary alcohols can have that hydroxyl group about a stereocenter. And these reactions are stereospecific. So we got to look at what exactly that's going to do if we know we have a particular stereochemistry. All right, we don't have to worry about that with primary alcohols. But with secondary alcohols, what we're going to see is what's called a stereochemical inversion. All right, this was a type of stereospecificity that we saw a lot in these substitution reactions. If we start out with that hydroxyl group on a wedge, when it reacts, there will be a stereochemical inversion so that now my new functional group, my chlorine, is on a dashed bond. So primary alcohols, we can convert them to alkyl halides using these two fancy new reagents. We can do the same thing with secondary alcohols, but if it's a secondary alcohol with a specified stereocenter, I got to note that there's this stereochemical inversion. Cool. All right. We're going to kind of skip tertiary alcohols for right now and come back to it. It turns out that in your mind it's helpful to have primary and secondary kind of grouped together. They behave the same, and tertiary to kind of sit in a little bit different of a bin. They don't behave the exact same. All right? So importantly, what we're going to note from here is that now we have primary and secondary alkyl halides and primary and secondary alkyl halides will undergo substitution with strong nucleophiles. All right, so let's just take a look at some strong nucleophiles. Nucleophiles are, remember, when you think about nucleophiles, the most important thing to sort of remember are these are electron-rich species or are electron-poor species. Nucleophiles are the ones that have a bunch of electrons, are electron-rich species. So then all of our strong nucleophiles have this one structural feature in common, that net negative charge. Right? So we talked about strong nucleophiles can have this formula RO with a minus sign. Or N with the minus sign. All right, we can have carbon nucleophiles. I guess it's actually R2N. Okay, so let's just take a look at some examples here. We got oxygen nucleophiles. Nitrogen nucleophiles. For our carbon nucleophiles, carbanions are pretty unstable except for in some specific circumstances. All right, one of which is the cyanide ions, so carbon triple bonded to nitrogen. This is a particularly stable carbanion because of that triple bonded nitrogen can help accept some of that electron density through resonance. Okay. We also have just terminal alkynes. We know how to deprotonate to create nucleophiles. So carbon-carbon triple bonds. And then there's actually a new nucleophile, a new carbon nucleophile that we just learned about maybe last week, at the end of last week. And those are our Grignard reagents, right? So we also have these magnesiums bound to carbon, which is also an example of a carbon nucleophile. Okay, so anytime we see oxygen with a negative charge or nitrogen with a negative charge, those are strong nucleophiles. If we have those carbanions are pretty rare, but we got a few special cases here, as well as our new fancy Grignard reagents. All right, and then lastly, we also see sulfur nucleophiles. And the one thing to note about sulfur nucleophiles is that they can be negatively charged. Those are good nucleophiles as well, but so are neutral sulfur nucleophiles. Sulfur is the one element that is just very, very good at being a nucleophile, even if it is neutral. Okay, so our primary and secondary alkyl halides will undergo substitution with strong nucleophiles. All right, so then let's just put in this same list here so that we can compare and contrast what our weak nucleophiles are. All right, so again, if we're looking at oxygen nucleophiles, but we're talking about weak ones, well, these are just simply oxygen nucleophiles that are not quite as electron rich as our strong nucleophiles. Our strong oxygen nucleophiles all have these negative charges, so our weak oxygen nucleophiles are simply going to be neutral. So an alcohol would be an example of a weak oxygen nucleophile, Water is an example of a weak oxygen nucleophile. Right? Our weak nucleophiles are neutral. Right? And I guess we can even say neutral except that one element that's particularly good at being a nucleophile, even if it's neutral, which is what? Sulfur. All right, but we can also say our nitrogen nucleophiles. Again, strong nitrogen nucleophiles are nitrogens that are negatively charged. Weak nitrogen nucleophiles are simply going to be neutral nitrogens. Like an amine or ammonia. Notably, we don't have any weak carbon nucleophiles because unless carbon has that pair of electrons, it cannot do any attacking as a nucleophile, right? You got to have some electrons to be a nucleophile and do some attacking. Neutral carbons have 4 covalent bonds. They don't have any electrons that can do that attacking. Okay, cool. So, again, we can convert our alcohol into an alkyl halide and then treat it with one of our strong nucleophiles to get our substitution reaction. Okay, so let's just take a look at some of those here. These are then necessarily going to have to be multi-step. All right, but let's say that I take my alcohol. I'm going to treat this with PBr3 and then an alkoxide ion. All right, everybody take a second and tell me the product of this reaction. All right, so I'm just going to break it up into steps here. That first step will convert that hydroxyl group into a bromine. And then I'm going to get my substitution reaction. Substitute that bromine for now this ethanoate over here, right? So to be clear, my 3 carbons in my alkyl bromide, originally in my alcohol, are now attached to my alkoxide ion, and importantly, that new bond is between that nucleophilic oxygen and that carbon bound to my halogen. Okay. One thing to remember about these substitution reactions of alkyl halides, this was a big topic in the first semester, all right, but importantly, when we have primary or secondary alkyl halides, that substitution mechanism all happens in one step, what's called an SN2 mechanism. Substitution. Rather, SN2 specifically means that your nucleophile attacks and your leaving group leaves in that same step. All right, so as we said, alkyl halides will undergo substitution with strong nucleophiles, and we're going to remind ourselves these are SN2 mechanisms. All right, so now let's play the same game, but we're going to do so with our stereospecific secondary alcohol. All right, and we'll treat it with the same PBr3 and then that ethanoate. Hey, everybody take a second, see if you can't give me the product of this reaction. So again, let's look at these two steps separately so that we can make sure we can tell what's up here. After that first step, importantly, we have this stereochemical inversion, so that now our bromide is sitting on a dashed bond instead of a wedged bond. But then we're going to note that when we do this substitution reaction, this is an SN2 mechanism. All right, and what you would have learned about SN2 mechanisms is, yes, they happen all in one step. The nucleophile attacks and the leaving group leaves, and a consequence of this is another stereochemical inversion. So in the first step, it gets flipped from a wedge to a dash, and in the second step, it gets flipped back to that wedge bond. All right, two back-to-back stereochemical inversions. This stereochemical inversion, it also happens with the primary alcohols, which are converted to primary alkyl halides. It just doesn't matter because these are not stereocenters. So you don't see that inversion happen like you would if you started out with a stereospecific molecule. All right, cool. So for the sake of practice, let's just do one more here. That's our stereochemistry pane. right, so that first step is going to flip that wedged up, that dashed bond to a wedge. But then when I have my second nucleophilic substitution step, it's going to flip it back to one of those dashed bonds. Okay. Cool. So what we're going to see with these alcohols is that we have a really hard time converting them into other functional groups because that OH group is a bad leaving group. So every strategy that we're going to have here is all about making that OH group into a better leaving group. All right, we've talked about one of those so far, which is to convert it into an alkyl halide. Those halogens are great leaving groups. So if I can swap out that OH group for a halogen, voice crack, then I can trade it for anything else. All right? Cool. So now we're going to have a new method for converting that into a good leaving group. Converting our OH into a good leaving group. All right, strategy 2 is going to be use what's called tosyl chloride. This is a very specific reagent with one job, and that is to convert that OH group into a good leaving group. It is this big fancy molecule that is specifically used for that purpose. All right. So this thing, I mean, just to look at it, honestly, we're going to abbreviate it in our structures quite a bit, but just so we know here. It's benzene with a methyl group on one side, and then this like thionyl chloride group. Okay. We abbreviate this big monster structure here as just TSCl. Okay, and just to kind of show it, we're going to use that abbreviation going forward here, but just to kind of show when we react our alcohol with this tosyl chloride, this whole thing right here is going to stick on to that OH group. Really, I guess just the O. Okay, so we can see it just kind of binds to that oxygen in my hydroxyl group. We could draw out the full structure, but again, we get lazy and we just say OTS. All right, and what's really important to note is that this thing here that you just created, that OTS group, is a freaking fantastic leaving group. All right, using this compound here, again, its whole claim to fame is turning hydroxyl groups into good leaving groups. That's because it binds to that oxygen and creates just a fantastic leaving group. That can easily be substituted out with one of our strong nucleophiles, just like our alkyl halides. All right. There is one big difference here. I used a primary alcohol. Let's take a look at one of those stereospecific secondary alcohols. All right, importantly, because our tosyl chloride is not reacting with that carbon, with that stereocenter, but rather just binding to that oxygen, what we will see is that there is no stereochemical inversion when we convert that oxygen into that good leaving group. Cool. All right. So then let's compare and contrast these two methods here. If we take this stereospecific alcohol and we react it, we're going to do our first method of converting it to an alkyl halide and then adding in some nucleophile. What would be the difference if instead we used tosyl chloride and then added in that same nucleophile? So in our first example, we get one inversion in step 1, followed by another inversion in step 2. So we flip and then flip right back. All right. However, in our tosyl chloride method, that first step does not lead to a stereochemical inversion. So then when we do our SN2 reaction, we will get a flip to that dashed bond. All right, so importantly, no inversion in that first step, but we do have an inversion in the second step when we use tosyl chloride. If we use our alkyl halide method, both of these steps will lead to a stereochemical inversion, which is why it flips and then flips right back. All right, so we said that we were going to keep the tertiary alcohols kind of separate in our mind here. So let's talk about these tertiary alcohols. All right, what is important to remember, this kind of common theme that's going to make these different from our other ones, is that tertiary carbons with good leaving groups will form carbocations. All right, so what do I mean by that? Let's say that we have a tertiary carbon that has this good leaving group on it. And I'm just going to leave this good leaving group as Lg for good leaving group. All right, what happens in what's called an SN1 mechanism is that leaving group literally just falls right off. Okay, leaving you with a tertiary carbocation. Now, this reaction right here is certainly in equilibrium, and that equilibrium will very strongly favor that more stable with the leaving group on compound, but there is enough of this reaction that occurs that this dominates the chemistry of these tertiary carbons right here. Enough of them will sort of fall apart and form carbocations that are then able to react with whatever else in solution to propel this reaction forward on actually a pretty remarkably quick timeline. All right, so even though if we looked at the equilibrium constant here, it would favor that more stable species, we still get a good amount of this carbocation that's formed, and that drives this reaction forward. Cool. So then if we took a tertiary alcohol and reacted it with that tosyl chloride, this would take that alcohol and turn it into a molecule with a really great leaving group. Which will then form those carbocations that we can react with any of our nucleophiles. And importantly, we're going to note that we can also use, and actually is preferable to use in many circumstances, are weak nucleophiles. All right, so this tosyl chloride is going to fall apart here and form our carbocation. Really, it's in equilibrium. All right. If we react that with one of our weak nucleophiles, like ammonia, okay, importantly, by the end of this reaction, that neutral nucleophile will have lost one of its hydrogens when we form our new compound here. Okay, so let's just note that our neutral nucleophiles lose a hydrogen in these substitution reactions. So I start out with NH3, but in order to form my neutral amine group in my product, I have to lose a hydrogen as well. Okay, so we can use the tosyl chloride. We can also convert these to alkyl halides in order to do substitution reactions, but it turns out that our fancy reagents, I don't know, honestly don't know if they just don't really work or if there's one way that's just so much easier and cheaper that is the way to do it. And we're going to see this strategy a few times, right? We talked about how we need to convert OH to a good leaving group. right, so this is our method 3, which is going to be to convert OH to this good leaving group water by using acidic conditions. All right, so if we have a tertiary alcohol and we just add in some HCl, that strong acid HCl is going to protonate that hydroxyl group. And now we have this good leaving group, which is just going to fall off of that tertiary carbon to create that carbocation. Okay, and that carbocation can react with those chloride ions in solution. To form our new alkyl chloride. All right, so we're going to see this next class as well. This is a pretty common method for getting rid of that hydroxyl group, is to use these strongly acidic conditions. Because in the presence of a strong acid, we protonate that OH group, and now it's a great leaving group. Now it would leave not as hydroxide, which is a strong base, but it just leaves as water, which is neutral, which is a great leaving group. Right? So what we kick off here is just a molecule of water, which is not a strong base. It's a perfectly fine neutral leaving group. Okay. One more thing to note about the consequence of these intermediates here, these carbocations, would be if we did this reaction with, now let's do a stereospecific tertiary carbon. Okay, so here's my alcohol. Now it's got that stereospecificity. All right, we'll show our mechanism here. Again, we're going to protonate that alcohol. Because it's on a tertiary carbon, that good leaving group just kind of falls off. All right, but importantly, what's formed here, this carbocation, carbocations have this perfect trigonal planar geometry here. Right, so we lose any of our stereospecificity. Meaning I started with all these dashes and wedges, but as soon as this carbocation's formed, now I'm no longer going to have a stereospecific reaction. My chlorine can attack this flat carbocation from either side. Can go from this end. Can go from the back end. And those would give me my mixture, my racemic mixture of all possible products here. Okay, so in our last step, when we have that chloride ion attacking and we draw our product shouldn't have any dashes or wedges, but just these straight lines. Okay, so these straight lines show no stereospecificity, indicating we have a racemic mixture. Okay, so the bottom line is with these tertiary alcohols, because they go through this different mechanism, they're not undergoing the SN2 where the leaving group leaves and the nucleophile attacks all in one step. They're having this two-step where they form the carbocation intermediate. They're going to lose any stereospecificity that they start out with in that process. Those carbocations are no longer stereospecific. Cool. All right, we got one more category of reaction for alcohols next class. Please come up. I got 4 unclaimed exams here. If you did not get a grade in your grade book for exam 1, please claim one. What's up? Daily quizzes? Yeah. Oh, okay. I'll check it out.
It was one on like green chemistry.
Oh, shit. That's right. We were supposed to do that today. Okay, great. Well, that'll be our Friday one. I'll push that one back. I'm sorry. Yes, please do. Yep. These are the unclaimed ones. Yep, these are the 3. Okay, will you put your name on it for me here? Yep, thank you. Thank you. This one? Cool.
I thought since it had it on the yellow page that it was gonna
So they separate them all when they give them to me.
Okay.
Thank you.